Hi, everyone. Thanks for being here this morning. We are here to listen to Jason Kulatunga about using graph theory to to empower patients and to answer questions. So thank you, and take it away.
Perfect, thank you. So my name is Jason Kulatunga. I'm the founder of Fasten Health. It's an open source, self-hosted PHR, so personal health record. And today I'll be doing a presentation titled Using Graph Theory to Empower Patients and Answer Questions. All right, so who am I? I've been in the industry for about 12 years as an infrastructure engineer, primarily responsible for designing HIPAA, SOC, PCI, and FedRAMP compliant architectures. Recently, I went to urgent care as I was having trouble breathing. After that, I was sent to the ER where they detected liquid in my lungs. Through those tests, they found an underlying chronic condition, and I came to understand that my medical history is a lot more complicated than I realized.
Jason, I'm sorry, you have something on your screen that'll show.
All right, give me a second. There we go. So doctors wanted immunizations, a family history, historical blood work. I generally knew this information, but not off the top of my head. Adding to this complexity was the fact that this information was distributed across the many healthcare providers I'd used over my career. Every company I joined was a new medical, dental, and vision plan, usually with a whole new set of healthcare providers. I'm also Canadian, so some of that information is not just in another institution, it's another country completely. There we go. Given my chronic condition, I wanted my healthcare data to be easily accessible. I didn't want to have to relive this experience with each new provider or career change. I started looking into existing products and solutions, but nothing out there did everything that I wanted. In general, healthcare record keeping sucks as a patient. Doctors and clinics have EMR systems, but there's very few tools out there focused on the patient. The ones that exist are concerning. In general, HIPAA protections don't apply once you share your medical data with a third party. They can effectively monetize and share your medical data without your consent. I wanted a tool that would aggregate my data from multiple healthcare providers like insurance companies, hospital networks, clinics, and labs across the multiple industries, so my vision, dental, and medical records, all in one dashboard. I wanted it to be automatic, able to pull my personal health record directly from the various insurance companies and hospital networks. And I didn't want to scan physical documents unless I had to. Lastly, I wanted it to be open source, something that I could evaluate and contribute to myself as I'm a developer. Leveraging the open source community means that the tool could integrate with hundreds of thousands of healthcare providers in the United States, making certain that even the smallest healthcare institutions could be supported. I posted my thoughts in a mock-up of the application on Reddit in a niche subreddit called r/self-hosted, which is a forum for users to share usually open source tools that you can run on your own server, instead of depending on SaaS or cloud solutions. The post was incredibly popular, making it one of the most upvoted posts ever, and there was a strong interest in what I wanted to build, and we started to gather a very diverse community. It was not just technologists, but doctors, lawyers, government policymakers, healthcare consultants. They all wanted to have conversations with me about how Fasten could serve their communities. And as we started building Fasten, I realized there was a series of common questions that users and patients wanted answered. Making sure that Fasten could answer these questions became one of my primary goals. So what were these common questions? They were fairly common, innocuous questions like, what is my medical history? What are my past illnesses, surgeries, and medical procedures? What are the current medications I'm taking? How long have I been on them? And what dosages was I prescribed? What were the results of my most recent lab tests? And how have my lab tests changed over time? What diseases am I immunized against? When am I due for a booster? What is my family medical history? What inherited conditions should I be screened for? And how can I find the contact information for the previous healthcare providers that I've worked with? So before we dive into how to answer these questions with graph theory, we should level set and make sure everyone's kind of on the same page. I'm going to keep the next section describing terms and technologies brief and high level, as each topic could and definitely is its own book. But hopefully it'll provide you with enough context to understand the final solution we're working towards. Okay, so first let me introduce a basic graph and the related terms to it. So we'll be leveraging those in this talk. A graph is a structure that consists of vertices, also known as nodes, and edges, also called links. It's primarily used to model systems and relationships. In this diagram, vertices, also known as nodes, are represented by boxes A, B, C at the top there. And edges, aka links, are represented by lines connecting the boxes. Next, I want to introduce the concept of graph theory. So graph theory is a branch of mathematics and software development that studies graphs and provides tools for analyzing and solving problems related to graphs and their relationships. There are a number of tools that graph theory provides, but the ones that we'll be looking at today are for graph representation, traversal, and clustering. Finally, there are a number of different types of graphs, but the type that we'll be leveraging for this talk is called a directed acyclic graph, a DAG. In a directed graph, the edges are connected so that each edge only goes one way. A directed acyclic graph means that the graph is not cyclic, or that you cannot follow a sequence of edges and end back at the same node, directly or indirectly. So note how in the second diagram, has directional arrows linking each node, showing that A links to D, but D does not link to A. And there's effectively no way to return back to A. This talk is more about the practical applications rather than the theory behind graph theory. So if you want to know more, you'll want to read a book. I'll link one at the end of this talk. Next, I want to introduce something that we're all familiar with, FHIR Resources. And as you know, they've become the effective standard for healthcare data exchange. What makes FHIR powerful is that it can be used to represent incredibly complex healthcare scenarios in a machine-readable format. So example, a patient can be associated with multiple encounters, which are in turn associated with multiple observations, procedures, and practitioners. This is relevant to us because these relationships can be modeled and analyzed using graph theory, with edges representing resources, with nodes representing resources and edges representing the relationships between them. So in our examples, we'll be limiting ourselves to the US CDI core resource set, specifically R4 for consistency. However, these relationships and techniques that we're using can cross any FHIR profile or IG. Finally, if you're thinking ahead, you may be concerned that I'm advocating for a native graph database like Neo4j, which comes with its own technical trade-offs. That's not the case. These techniques are database agnostic and can still work with a relational database like Postgres or MySQL paired with a graph library. However, keep in mind that there are some performance and scalability constraints when generating graphs just in time. Since we're trying to answer questions for an individual patient, we've already constrained the raw FHIR resource count considerably, and with some caching and other optimizations, these techniques can work at scale. Longitudinal analysis spanning large patient cohorts may not be realistic at scale without significant performance optimizations. Okay, so with that context out of the way, let's dive into the meat of the talk, FHIR relationship graphs. If you want to generate a graph containing all FHIR resources related to an individual patient, the naive solution is to just model FHIR resources as nodes in a graph and their relationships as edges. Nodes A and B could be replaced with condition and patient, while the edge could represent the type of relationship, which in this case would be subject. This has a problem. I'm not sure how clear this diagram is, but the segments on the outside of the circle represent the different FHIR resource types, and the colored lines represent relationships between them. As you can see, graphing all FHIR relationships is effectively worthless. The graph is too complicated to understand any semi-complex relationships, and this is with each resource type being represented only once. Imagine the exponential growth when a user has multiple conditions with dozens of observations and practitioners. Another layer of complication is that the FHIR resource relationships are asymmetric. They're weakly connected. A procedure resource can reference a practitioner resource, but a practitioner resource does not reference all procedures. This relationship diagram doesn't even take that into account. Now think back to the first question that we wanted to answer. What is my medical history, which includes all past illnesses, surgeries, and medical procedures? trying to write a single SQL query to answer that question would be laughably complicated. So what next? This is where the DAG comes in, the directed acyclic graph. In graph theory, a source and a sink are special types of vertices or nodes in a directed graph. A source is a vertex from which all edges of the graph originate. In other words, it's a vertex with only outgoing edges and no incoming edges. A sink, on the other hand, is a vertex where all the edges of the graph terminate. It is a vertex that only has incoming edges and no outgoing edges. So if we zoom into a specific FHIR resource that we care about, we can represent its relationships as a directed graph. The resource would be the source, and its direct relationships would be sinks. However, this is still of limited use. Why go through all the work of converting a single FHIR resource relationships into a graph when you can just parse the data structure? To answer that question, let's look at a more realistic scenario. We have a patient that has multiple conditions. Condition A requires a visit to the doctor multiple times to diagnose and treat their condition. So maybe it's like a chronic illness like diabetes. The first visit, they visit a clinic close to their work where they had some tests done. And their second encounter was at a clinic near their home where they were prescribed some medication. Condition B required a single visit to a single location near their home where they visited their primary care physician, maybe for a sprained ankle. Trying to find the observations owned by a FHIR condition would be non-trivial, especially if you're trying to do it programmatically, taking into account additional layers of nesting, asymmetric relationships, and interaction. So remember, we're trying to answer that basic question. What is my medical history? What illnesses, surgeries, et cetera, have I had? If we take the scenario prescribed in the previous slide, but tag certain FHIR resource types as sources and others as sinks, then we can create a boundary around all the resources related to a source, effectively creating a group by clause spanning multiple related resources. This would allow us to take the full patient history and partition it by medical condition. Patients and healthcare providers, caregivers, could then see which medications are associated with which condition, the associated lab work and diagnostic imaging, et cetera. We're grouping by resources tagged as a source, creating a subgraph. Sinks are either our goal resources or pivot points where the subgraph would incorrectly connect to an unrelated grouped resource. So in this example, we want to group by condition, which is tagged as a source, and we'll tag shared resources like location, organization, practitioner as sinks. This results in two distinct subgraphs, each containing FHIR resources related to a single condition. And you can see those in the yellow. To implement this pattern in practice, we need to understand one final graph theory technique, adjacency and predecessor maps. So the adjacency map contains an entry for each vertex, and each of those entries is a list containing adjacent vertices. In a directed graph, only vertices joined by an outgoing edge are considered adjacent. The predecessor map also contains an entry for each vertex. However, it's the complement of the adjacency map, where predecessors are the vertices joined by an incoming edge. So if this sounds vaguely familiar, that's good. These definitions are similar to the way that we defined source and sink earlier. Any adjacency map entry with an empty list is a sink. So in this example, C and F, which only have incoming edges. While the predecessor map while a predecessor map entry with an empty list is a source. In this example, A, which only has outgoing edges. So we can use the predecessor map to find the starting vertices for our subgraph traversal. Basically, once a graph has been generated with all the correct vertices and edges, the empty list in the predecessor map tell us where each subgraph starts, and the empty list in the adjacency map will tell us where to terminate our traversal. Looking again at our realistic scenario, we can see that subgraphs start at condition A, which is a chronic illness like diabetes, and condition B, the sprained ankle, because they have no predecessors. Depending on the condition that we're interested in, We would then recursively process the adjacency maps until we hit a termination condition, an empty list. Okay, so now that we have all the pieces, we can finally discuss the generic algorithm. First, we start by retrieving all FHIR resources for a patient. Then, we add each resource as a vertex within the DAG. Next, we selectively add edges, links, between the vertices. Let's call them A and B. If vertex A or B is a source, the edge is directional from the source vertex to the other vertex. If A or B is a sink, the edge is directional from the other vertex to the sink vertex. All other relationships must be strongly connected, where we add reciprocal edges from A to B and B to A, even if they don't exist in the original sources. After all the edges have been added, we can find the starting vertices for the subgraphs using the predecessor list, looking only for empty lists. For each subgraph, start at the vertex and recursively follow the graph using the adjacency list. This is almost the exact algorithm that Fast and Health leverages to help us answer patient questions. It's language, database, and framework agnostic. So now that we've thoroughly discussed the algorithm and the technique, we can finally show how to apply graph theory to answer our original patient questions. But please note, the source and sink resource types listed in the following slides are not exhaustive. They'll be impacted by your FHIR profile or IG, so they require tweaking before you can apply this algorithm to your resource set. We basically solved our first question already: what is my medical history? As discussed, we can group by the condition, encounter, and explanation of benefits resources, and terminate on location, binary, device, org, etc. This provides us with a bounded subgraph that contain resources only related to a single condition, encounter, or EOB. Next, let's try to answer the question of what medications am I currently taking? We just apply the same technique as before. However, in this case, the grouping is done by the medication type resources and terminates on shared resources like organization, location, practitioner, and pivot points like condition, encounter, and EOB. Patients are generally interested in the condition or conditions their medication were prescribed for, as well as the prescribing practitioner, all of which they would get with a single request, no matter how deeply nested the transitive relationships. Next, let's create an address book of important contacts and healthcare providers. Patients generally want to know where and when they last interacted with their practitioner, in addition to the conditions they were treated for. Grouping by resources like practitioner, organization, location, and terminating on pivot points, which are basically all other resources. Again, the nice thing about these subgraphs is that we get the additional benefits of finding the related procedures, encounters, and conditions without a sophisticated SQL or Neo4j query. It's worth noting that when you're holding a hammer, everything looks like a nail. So while graph theory and directed graphs can help you solve problems involving complicated relationships, in some cases it's overly complicated. For example, when we're trying to generate an immunization history, it's simpler and more performant to just query by immunization resource type. So in the software development world, reinventing the wheel is usually frowned upon. While it may sound like this application of graph theory is solving a problem that's already solved by your clinical data repository, CDR, or graph database, there are a number of benefits achieved by introducing graph theory into your existing application and tech stack. The FHIR Search API is optimized for searching within resources and nearby resources, not deeply transitive relationships. There's also a requirement that relationships between resources are known beforehand to use the _include parameter. This is also true when building a DAG that we've been discussing. However, the relationship processing and extraction can be done and cached in the database. On the other hand, a CDR doesn't usually expose these relationships, requiring developers to build complicated recursive parsing libraries to exhaustively find related resources. Effectively, you can dynamically create a patient everything or docref query for any resource type, which is incredibly powerful when paired with a CDR. As discussed earlier, when pairing graph theory with FHIR resources, as discussed earlier, pairing graph theory with FHIR Resources does not require a graph database like Neo4j. However, it does require persistent storage of some sort. Relationships between FHIR Resources need to be extracted and stored. However, this can be done during insertion at the expense of additional storage and indexing compute rather than at runtime query time by the user. This allows it to benefit heavily from caching, which can be very performant. If you're unwilling to generate graphs on demand and manage the associated caching in application code, you may want to consider a dedicated graph database like Neo4j. It's designed for relationship graphs with an ergonomic query language that can easily find clusters of related resources with a single query, unlike the FHIR search API. You also gain additional benefits of caching at the database tier. So this application of graph theory is not novel. However, I haven't seen it discussed widely in the FHIR client space. This may be due to the fact that it's computationally expensive for large data sets, like longitudinal studies. However, for individual patient records, like those available under the the Cures Act final rule, it's incredibly valuable. All right, if you want to learn more about how we're applying graph theory to answer patient questions in our open source PHR Fast and Health, you can take a look at our GitHub repository or join us on Discord. We currently support approximately 10,000 healthcare institutions in the US, with more being added all the time. For those of you interested in pulling data from international healthcare providers, please get in touch. We're currently exploring how to retrieve healthcare data from international institutions, and we need guinea pigs. If you want to support the project, please consider giving it a star on GitHub. It really does help with exposure and social validation. And as most of you are developers, you can contribute. Finally, for those of you in Zoom, I left my email and Calendly link. I'm in San Francisco if you'd like to chat in person. Thanks. Any questions?
Yeah, just one moment. So thank you so much. You got through 30 slides in less than 30 minutes. It was very impressive. So we have a little bit of extra time for questions. I'm going to come around and pass you the mic. I just ask that you speak very clearly because there are people online who are listening to this as well. Yes.
Thank you for the talk. Can you show some real query? I mean, a real graph query you're really doing? And what language are you using to describe this query?
So I use Fasten's written in Go, but we're just using a standard graphing library. The query isn't really complicated. It's basically generation of the graph that's the complicated part. Querying it is basically just looking at the predecessor and the adjacency maps and then recursively following the path until you hit an empty list. So it is kind of processing intensive, but you can cache the result depending on how frequently you're updating your resources.
Thank you. And another question, are you tagging ages with the attribute names? Or
am I taking ages with attribute names?
Yeah, in your graph, yes. So if we have reference from one resource to another resource, it usually starts in some element which has a name, yes, and has some specific semantic, because you may reference the same resource from another through the different ways.
Right.
Are you using these attribute names in your graph? Or is it just pointing?
So the graph is made, it doesn't actually contain the resource itself. It contains the identifier for the
Does
resource.
it contain the name of element where the reference is?
Observation performer versus observation subject.
Yeah. Do you distinguish
Sure.
between?
You can. We don't.
Okay.
So you can do that. You can weight your links. There's a whole bunch of additional complexity to that, but you can weight your links. You can also create additional kind of related to fields, like additional metadata for the nodes. You can get that metadata out of the graph. We don't currently leverage that.
Okay, thank you. Because it may be negation. So
Sure.
Thank you.
Jörg Bleuer from Switzerland. Thank you very much for your excellent talk. The interesting point is then that you can qualify the metadata of the edges as vertex themselves, and I think that's possible in this graph database where you. Is this right?
It is, again, not something that we've currently investigated, so I can't tell you what the implications are of that. But yeah, there's certain types of graphing libraries give you additional functionality, and so the graphing library that we use in Go does allow us to add metadata to the edges themselves, as opposed to having to create a whole vertex for it. However, depending on the language, depending on the graphing library, that may not be true.
I mean, the issue is that if you see at the ontology like SNOMED CT, for instance, then you have, between concepts, you have relations, and you have different qualities of relations. And in SNOMED CT, these relations themselves are, again, concepts in CT, in SNOMED CT. So that's exactly what's done there as an abstract model. And I think if you put that in a graph database, that's it.
Very interesting. I'll have to look into it. Thanks.
Thank you. This is a really nice talk. And I love that you started with these examples of questions that your end users want to ask. And then you gave this structure about how these breaking down graphs in this way can help answer the questions. Do you have an example of how those graphs surface in Fasten's user interface to help people browse through their data? Like, where do those things land?
I do. I'm not sharing my desktop, so I'm not sure how this is going to show up for people in Zoom. So give me 1 minute. All right. So if I go to the GitHub URL, github.com/fashion-on-prem, and then I move this over here, and there are screenshots. There we go. Okay, so specifically for the data that's coming out of these queries, this graph parsing, this would be a good example. Maybe not. All right. I don't have a good one for you, other than to say that this is not very clear. What you're seeing here is a condition. Within that condition header, there is all the associated practitioners. Further down, there's a patient-friendly description for that condition. On the right-hand side, actually, if I scroll further up, there would be additional kind of associated resources for that condition that can't be grouped on the left-hand side. And then on the right-hand side, which is hidden by this overlay, you can see the procedures that were done, the tests, any sort of like lab work that was completed, as well as medications, if there were any, would show up there. And so this is all generated from the graph, and then this would be one specific subgraph for that condition.
Awesome. Thank you.
Yeah. Okay.
Hi, thank you for the presentation. Actually, a couple of years back, I've also used direct acyclic graphs with PostgreSQL for basically reverse include and hazardous chaining to support those kind of things in the FHIR server. There is every resource entry with a lot of references will blow up your graph table, right? How do you plan to index those? And it keeps on growing. That's what I faced when I developed it. And indexing was quite a job. And also, what is the depth of the graph? How do you find out if it's not cyclic? Like I think I had to put some 5 or something as the maximum vertices that can be created.
Okay, let me answer your first question. It can get complicated, given I showed the diagram with all the different resource types and all the different interconnected connections between them. So yes, there's a large number of different relationships for these FHIR resources. However, the specific solution that the specific problem that we're solving is for an individual patient, and that significantly limits the scope of the problem. The number of FHIR resources that we need to process at any one time to generate this graph, even on demand, is fairly reasonable. Even when you're talking about, I think in the order of, I want to say about 10,000 different FHIR resources for an individual patient, fairly reasonable. And I hope that answers your first question.
Yeah, because I was developing it for a EHR use case.
Right.
Around 30,000 patients was blowing up of more than 1 million records in the edge table.
Right, but the thing that's interesting here is we're grouping for an individual, right? So you don't usually have that problem of these millions and millions of records and all the fan out in terms of, the exponential growth in terms of relationships. It's a much more scale-friendly solution. Yeah, and then to your second question, sorry, I kind of forgot already.
No, so the order of the indexes, so if there is, say, which resource actually created this entry is also important if you do reverse chaining, right? So what level of depth do you go when, say, a procedure request points to a condition, and then that condition, there can be a patient reference in the condition, and if you want to do reverse chaining and also achieve that using the graph, what is the level of depth?
Okay, so that's partially solved by the DAG. When you create a DAG, you basically have, at least the graphing library, again, the graphing library that I was able to leverage, had this functionality where it enforced the acyclic part of the DAG. What that means is if you try to create a cycle, it won't add that connection. And so I don't need to worry. I can actually exhaustively, recursively search the adjacency map. Any other questions? Oh, all right. I'm glad I went quickly.
Does Fasten, you said it integrates with 10,000 healthcare systems in the US or something? Does it have like definitional resources, plan definitions and profiles? Like how does it interact with that at all or not?
Plan definitions. Sorry, I'm not familiar
Like the
with
content side that might, define the meaning of some of these patient-specific resources.
I see. So Fasten integrates with U.S. healthcare providers under the U.S. core CDI IG. I think IG, or at least profiles. And what that basically means is there's a known set of relationships and resources. So
Separately download those profiles as part of like Fasten.
right, and then I generate a model, and then I can use that for deserializing and serializing the data. Yeah.
Thanks, Kate. Thanks a lot for the presentation. It was pretty interesting. Maybe I missed this information, but what is the difference between an EHR and Fasten Healthcare?
So
Oh,
it's-
do you would use both or?
So this is patient focused. This is for a patient like myself.
Yeah.
You can imagine a future where it runs on a laptop or a phone or something like that. But the idea is that I can create my own longitudinal medical record by pulling in all the different bits and pieces of my medical record that's stored in various healthcare institutions across the United States. So for certain countries, like in Canada, there's one central repository. My understanding, at least. Sorry, someone here probably knows the truth. But my understanding is that there's one central repository for my whole medical record, and I could query one API to get it all. Unfortunately, in the US, that's not true. Each different medical institution or healthcare institution has their own FHIR server. And so what that means is for a patient to collect all of their medical information and store it in one place, they have to be able to talk to all these different healthcare institutions. And that's what Fasten does.
Okay, perfect. Then a second question. So the customers are the patients, the
Yes.
individuals.
Yes.
Okay, and what do they do? do they do a subscription, or how can they?
Right now, it's open source. It's
get
open
this
source,
service?
and you can self-host it. It's a Docker container. In the future, to be quite honest, this is not something that my parents could run. Right? They're not familiar enough with technology. They don't have a home server. Docker isn't a thing that's even in their vocabulary. So what that means is it has limited impact. Right? In the future, I know that there needs to be some sort of SaaS model, but for right now, I think given the significant changes in the healthcare space, and given the growing, or the significant number of different healthcare institutions that we need to integrate with, it's okay for it to just be for technologists. It's still very, very early in its development cycle, and then we can figure out how to make it a SaaS platform to open it up to the general public in the future. But right now, self-hosted, it's really for developers and people who are, on the cutting edge of, or really, really interested in their healthcare record.
Okay, yeah, cool. Thanks a lot.
Thanks for your presentation. You didn't talk about financial data at all. And from my perspective, this could potentially shed light on some of the market forces. For example, one time I had a procedure and my health insurance company sent me a letter that said, hey, this doctor's trying to charge $30,000 for something that should normally cost $3,000. Having the ability to see your claims and potentially also your explanation of benefits would be interesting. Claims you should be able to get, theoretically. It's not part of US Core, but that's okay. You should still be able to get it from an EHR. But what are your plans around that?
It was something that was brought up in a GitHub issue. I haven't looked into it, but it is something that has been discussed, and I can obviously see the value of it as well. But it might be a while. Yeah.
If I understood the approach for actually constructing these graphs, it's based on instance data. So you've got a whole pile of data about an individual, and you just traverse those instances, figure out the adjacencies, and produce the subgraphs. In theory, you could do something similar at kind of a static level, just looking at the FHIR resource definitions themselves and saying, to construct condition subgraphs, I'm going to start at condition, I'm going to follow the condition.subject link, and just describe those links that you would follow. Mm-hmm. There's this FHIR resource called graph definition that can sort of say things like that. Have you looked at it? What's your sense about whether it's useful?
Not familiar with it,
Okay.
So can't answer that, sorry.
No worries.
Might want to talk with you afterwards about it, though.
Okay, and I'm not trying to sell you on it. I haven't used it for anything useful myself.
Okay.
So I'm a patient, not a developer, and I'm very interested in the approaching world of pulling together all my disorganized garbage from 5 different hospitals. And so I hear you so this sort of middleware, right, that will do some sort of pulling it together. What would be a next step that would be necessary for me to be able to make use of that? Some sort of, could there be, or maybe there already is, some sort of PHR that would harmonize or aggregate all these things and let me see what you found? Because right now, the one simple app that I've tried to use brings me essentially 5 different disorganized piles of paper in electronic form.
Right. So this does, so when we generate the graph, we don't care about the source, which means I don't care if it came from your hospital. I don't care if it came from your lab. I don't care if it came from your clinic, your urgent care. It aggregates it all together, and as long as there are connections between, as long as there are connections to that underlying condition, it will correctly put it under the correct umbrella. In general, because you're talking about different healthcare institutions, they won't tie or they won't roll up to the same condition. And as a user, what you can do in Fasten is you can actually say, hey, this condition from this healthcare practitioner, this hospital, let's say, and this condition from this urgent
Right.
care that I went to are the same thing. And I can merge them. It doesn't actually merge them because under the hood, FASN never modifies your healthcare information. But what it does is it creates an additional link with a kind of a wrapper resource. And so now you have control as a patient in how you visualize your data, as well as when you actually go to the UI, it'll show you that condition box that I was showing would actually potentially be coming from multiple different healthcare institutions.
I'll come see you.
All right.
Okay. Any questions online? Nope. All right. So Jason, thank you so much. This was a wonderful presentation and generated a lot of talk. So this was excellent. Thanks.
Thank you. Hi.
The guy